Hello everyone. Today is my great honor to present the findings of our research project funded by PSAP UI/UX program. My name is Eric Jindu. I'm from University of Florida, and we have collaborators from Northeastern University, Dr. Ran Wang and Dr. Yinzi Lin, and from Texas A&M University, Dr. Patrick Sherman. So our project is about the development and the test of a personalized wayfinding information system for firefighters based on the real-time cognitive load measures of them. We focus on firefighters because we do see the urgent need of protecting the heroes who are protecting us. According to the FEMA and the NFPA data, in 2018, there were more than 1.3 million fire-related accidents. That means one fire accident every 25 seconds. They caused more than 3,600 deaths and more than 15,000 injuries. If you go deeper into the data, you would say the majority of the injuries were related to firefighters themselves, more than 58,000 firefighter injuries in the line of duty. And there's a reason for that. At this point of time, there are about 1.1 million firefighters in the US, but 2/3 of them are volunteers. There's a significant shortage of firefighters. There's a lack of training method, training funding. So there's an urgent need for us to see how we can better help them. Of course, if you check the causes of firefighter injuries and deaths, there are so many different reasons. But there's a significant one that we would love to focus in this research project: disorientation. Many times it's not difficult for the firefighters to find the way in a burning building, but because they are unfamiliar with the building, because of the stress level, because of the low visibility, a lot of times it's very difficult for them to find the way out of the building. They are trapped. In fact, about 43.6% of firefighter injuries were somehow related to disorientation. In fact, if you check the problem, it's probably more complex than you thought. A lot of people would think, oh, the disorientation in a building is all because of the buildings are becoming bigger and the layout are becoming more complex. So I'm pretty sure that a lot of people got lost before inside a casino, including myself. This is a picture of a casino, and this is the layout of the same casino building. If you check the layout, check the map of this casino, it's actually not that complex. It's actually very simple, symmetric, and well structured. So the things that caused us lost is actually not the layout, but all the signage, the colors, the lights, the moving people, and even the background noise. It's actually the cognitive overload that stop us from finding the right direction. In fact, modern buildings, of course, are becoming more and more complex. So researchers and industry practitioners, they are trying their best to see how we can better transfer the information to you, how we can better visualize the complex building for you. So we use the fancy computer technologies to build a 3D model, virtual reality model, augmented reality model. But we need to really step back and ask ourselves, do the firefighters appreciate that? What if a firefighter is really adapt to the traditional 2D map instead of that fancy augmented reality goggle? What if giving them the visualized information, giving them the most fancy technology would only overburden their mind? There's a need for us to check their cognitive fingerprint and decide the best solution for each individual. In fact, this practice has been very popular in other areas. For example, Facebook. Open the Facebook, you will see the feeds only based on your own preference, because Facebook learns from you. Facebook knows you, so it personalized the information for you. And the same thing applies to Google. If you and me Google the same keyword, we would see totally different returned results, because while we are working online, while we are browsing things, Google learn our behaviors. So when we are facing the dramatic amount of information, the technology help us filter the right information and show the information in the right format for each individual. Unfortunately, if you check the ER community, we are still giving the same thing to every ER, to every firefighter. Um, don't appreciate their individual preference in terms of information format and the way to show the information. That is the motivation of our research. So our long-term goal is to develop and test this personalized information system, which we call Cog-DNA, to control the real-time cognitive load of firefighters in emergency wayfinding. And everything should be based on their individual difference in information preference, measured by their brain activity, measured by their physiological metrics, which we call information personality. So a natural question is, what options do we have? What we can adjust to personalize or to control their cognitive load? In fact, no matter what you think, we are relying on three types of information to know an environment, to learn a building: landmarks, routes, and a survey. The landmarks is more kind of like the signage. For example, oh, I anchor my memory about this building based on certain curtain or based on this certain plant. Route, it means I start to connect the points and I try to remember how I go to this particular office by turning left or turning right. Survey knowledge is more kind of like a cognitive map, like a map building your mind. So you stand here and it somehow feel, oh, the pharmacy should be at my left hand side, and that particular grocery store should be the right hand side. So there's three ways to show the information to a person. And for each of them, you have different formats, to show. For example, it could be phonological or verbal. For example, go 300 yards and then turn right. That's a verbal way to show the route spatial information. Or it could be visual spatial information, like giving them the map or giving some written structure instruction to them. Or it can be other sensory feedback. For example, we can definitely use a haptic device to show the vibration while we are closer to certain landmark. So we have different types of spatial information to show, like landmarks, routes, and survey. For each of them, we also have different formats to show. That gives us a matrix. And now imagine if I plot your most favored combination of them, and that can give you the lowest cognitive load, then we will have a landmark for you, which we call cognitive load landmark or information personality. Now, for you, you have your own landmark. For me, my landmark and landscape can be very different. So that is something we want to find out and optimize. So to achieve that long-term goal, we follow this 3-year research roadmap. So the step one was to develop a VR platform that can help us simulate the search and rescue activities and collect personal information. And that was done in June 2018 to June 2019. And based on that, we perform a lot of human subject experiments. So we get all the points on this landscape so we can have this complete surface of your landscape and better understand your information personality model. That has just recently been finished, and that's our last year activity. So in the new year, we will be focusing on the step 3. So based on everything we learned, we would love to prototype the system and see how we can intervene your information processing, wayfinding information processing in real time. So in the following slides, I'm going to go over all the 3 steps. Year 1 activity, VR development. So just want to show you the system we developed. So number one feature we would love to achieve is the simulation must be photorealistic. And this is just a quick view of the simulated fire smoke. As you can see, our simulation follows the physics. The smoke goes to the ceiling, bouncing back, the fire starts to propagate. So that's the number one requirement we learned from all the participating firefighters. Your simulation must be able to cheat us and make us to believe this is real. We also made the system adjustable or interactive. So imagine that as a coach that you can adjust the size of the fire, the color of the smoke, and the speed of the air ventilation just using an iPad.
Okay, smoke, faster smoke.
So in this way, our data collection can be really interactive. So let's say, depending on our current cognitive load measure, we do believe we need to switch you to less intensive tasks, and we can use this algorithm to automatically adjust the simulation and see how that will help you reduce your cognitive load. And of course, talking about the fire simulation, the hazard simulation is a very important part. So as you can see in this demo, we simulate the explosion, the fire, the smoke, but also we simulate the tunnel view that in case you got injured. We also simulate the increasing heartbeat to stress you a little bit. So based on the reflection, the feedbacks of the participating firefighters, they did believe this simulation was realistic enough for them to feel that they were in the mission. And of course, we are not just doing this VR simulation for training purpose. We are doing them, as I mentioned, for human data collection, so we can better understand your information personality. So in this case, while this firefighter was using the system for training, we use some built-in sensors to track the gaze focus, the heartbeat, ECG data, as well as the neural function. You can see the cap that he was wearing. So for us to better understand the behavior, once the subject was done with the experiment, we actually document all the personal data in an Excel spreadsheet, and we can play it back, as you can see later here. This is the playback of the gaze focus, so we can better understand how the attention focus pattern of this person. This pink line shows the gaze focus, and the green line shows the movement of that person, as you can see here. So this is extremely helpful for us to identify the most important landmarks and also calculate some statistics to see if this person was relying more on the route knowledge or the landmark knowledge or the map. And we also, like I mentioned earlier, we also collect the pupil size of this person and also the brain activity. So those are direct measures of their cognitive load. So other than this low visibility office building, we also, programmed and modeled different environment. Like you see here, this is a school building, and this is a weird subway subbase as basement, and this is an airport terminal with some passengers. So we develop multiple different scenarios, so we can definitely see the different impacts of the different built environments on the firefighter wayfinding performance. So that's the quick overview of our phase one, step one, year one activity. Year two, experiments. So based on the VR system development, so in year two, starting from summer 2019, we started to recruit firefighters to participate in our experiment. So special thanks to our collaborators from Brand Fire Department in Texas. So far we have done 50 firefighters, the experiment on 50 firefighters. As you can see, this is when they had fun in our system. And we collect two main metrics to understand their cognitive load patterns, brain activity using this device called fNIRS, and also the pupillary change that is directly related to their emotion and cognitive load. So this is the experiment we did mainly last year. It's a search and rescue experiment in a very complex office building. The mission, the task we gave to the participating firefighters was to find 3 missing people, A, B, and C, from this starting point. I don't know if you can see that, this green box here, that's the starting point. So they need to find the 3 missing people. And we do give, for the control group, they didn't have any information. So it's all based on their free search. And we do have other test groups. So for one test group, we gave them the landmarks that will lead them to the missing people. For the second condition, we gave them the routes knowledge. For example, you should go across 3 office suites and then turn left and then turn right. And for the third condition, we gave them the map, as you can see here, and we gave them only 3 minutes to try to memorize the map. And the fourth condition, we gave them this haptic suit that can vibrate in the right direction of the missing people. And for the last condition, we gave them simulated augmented reality solution that they would see a arrow floating in the air pointing to the right place. So finally, 50 firefighters participated in this experiment. All were male. 8 of them reported VR sickness and had to give up in the middle of the experiment, which is 16%, and which is kind of normal for VR experiments. And their age ranged from 23-year-old to 41, and the average age is about 31, with a standard deviation of 4.19. And their work experience ranged from 8 months to 17 years. The average is 7 years, and their BMI is 29.3. This is the procedure. So when they arrived on site, we perform a background questionnaire to collect information about their previous experience with search and rescue, their previous gaming experience. We ask that question because we do see when you play more video games, your spatial ability tends to be better than others. And then for most of them, they didn't have any VR experience before this experiment, so we do give them about 10 minutes to play with our VR system, so they can better know how to move freely in the VR, how to interact with different things in VR. And we perform this baseline study. So we basically perform this cube test and a memory test to make sure that they had similar level of memory ability and spatial ability. And also we perform this fNIRS and the pupil baseline study, so we can build their, like for example, the oxygen level consumption base of a person. Each person is very different, and also their baseline pupil size. So the changes can be will be comparable. And then they will be asked to perform an experiment. So we use something called within participation, which means each firefighters will be exposed to all conditions I described, like control group with no information given to them, landmarks, routes, survey, haptic suit, and this augmented reality solution. And in order to rule out the learning effects, so every time we change the target destination a little bit. And by the end, we perform interviews and questionnaires again, asking them about their experience, and we perform this NASA TLX cognitive load survey. So in terms of what was measured, we tried to measure as many as we can. So of course, the primary is neural activity. So as you can see here, we use a device called fNIRS. This device shoots infrared light into the brain, totally safe, 2 to 3 centimeters deep, and also track how much infrared light is absorbed in certain area of your brain. So based on that, we can calculate the oxygen level consumption in certain area of the brain. They also wear this VR goggle, and we do have this eye tracker built in. So this eye tracker can track where they were looking at, as well as their pupillary size change at a frequency of 90 hertz, so 90 data points per second. And also we track their like eye blink rate, eye movement frequency, and this ECG data. The ECG actually shows the pattern of your heartbeat and the electrical features of your heartbeat. So it's a great indicator to show if you're nervous or not. And this is just a quick screenshot of the fNIRS data we collected. As you can see here, on the right shows a higher level of oxygen consumption, and the blue shows a lower level oxygen consumption. You see the beating here? That's actually a heartbeat because it gives you that repeatable pattern. And in our analysis, of course, we remove that and we purely see like the trend of your oxygen level consumption. And because each area of your brain shows different function, which we call neurofunctional analysis. For example, the front side of your brain, which we call prefrontal area, is often related to memory retrieval or activity planning, higher level cognitive actions. The side of your brain, which we call motor cortex, that is the area that is coordinating your actions. So by checking how the blood is flowing across different areas, we can calculate, which function you are using more. And also by calculating the oxygen level consumption, we can see in general if you are more tired or not. And this is the fNIRS method we use. This is called GLM. As you can see, all the black lines here shows the oxygen level consumption over time. So X is time and Y is the oxygen level consumption. And you'll see multiple lines here. Each line represents one area of your brain. So we collect 24 areas. And we don't just simply calculate the average number. And in fact, according to the previous research, we do know how the oxygen level consumption would change over time if a certain area of your brain is activated. So we basically overlay the two figures and check the similarity of your brain curve and the pre-established brain curve we found on average people. And by calculating that, we know the percentage of activation. So let's say you are so similar to this highly activated brain oxygen level consumption curve, so we can know your area, this particular area is more activated, and vice versa. And like I mentioned earlier, we also track their like eye tracking and the pupillary size change. If your pupil is becoming larger, it means you're more tired. It means you're thinking a lot. It means cognitive overload. But the problem is your pupillary size is also impacted by the environmental light, like the lighting condition in the room. So we developed this innovative method. We calculate the RGB value of each pixel because you are wearing the VR goggle, right? So we calculate the RGB value of each pixel, and then we apply a set of mathematical methods to find out the latency of your pupillary change. Because if we increase the light, your pupil will become smaller, but there's a time delay. So we can automatically find out that. We can automatically calculate the luminance that is going into your eye. So we remove the light response from your pupillary change. The residue of your pupillary size change actually is showing your cognitive load. So just to give you a quick demo of how the system works, we actually made the system interactive.
This video shows a real-time cognitive load tracking system using the pupillary size of a person. As you can see, the upper one shows the real-time pupillary size, and the lower one shows the luminance, which is how bright the environment is. We calculate the RGB value of each pixel inside this VR goggle and convert that into the luminance. And we have a formula to remove the light response effects. So the residual shows the pupil size change driven by the cognitive load. As you can see, with this person moving around, the luminance is changing, the pupil size is also changing accordingly. All right, now we just ask this person to stare at the same place. And as you will see in a moment, the luminance start to stabilize. Now we ask this person a very tricky question, 133 times 55. Now we can see the luminance stays the same, but this person's pupillary size just increased dramatically, around 20%, and start to stabilize.
All right, so
This video
just a very interesting experience. We actually gave this demo at the CES
This video
2020 show this year. I was doing this experiment, and an officer came to me. So originally, I asked the officer to ask me some tricky mathematical questions. Unfortunately, my pupillary size didn't change at all. I was nervous because I was thinking, hey, I need to show our system is working, but then it doesn't work. Then the officer asked me, hey, Eric, have you ever violated the speed limit, but it was lucky and didn't receive a ticket for that? So everybody started to see a 20% increase of my pupillary size. So just to show you, the system is actually working. Okay, so this is a quick overview of the result that we discovered. So it's showing the information, landmark information, route information, survey information, and the control group, the comparison of that. So in terms of the wayfinding performance, we do see the route instruction was more effective than other instruction, like just telling the firefighters, hey, once you go into the building, turn right first and then go about 300 yards and turn left. This kind of instruction for most people was more effective than the landmarks knowledge and survey knowledge. But if you check their cognitive load, this is NASA TLX score. The higher means a higher cognitive load. What's interesting is this root knowledge wasn't representing the lowest load. In fact, the control group represented the lowest load. So we do see the difference between their perceived cognitive load and their actual performance. We don't know why. That's why we started to dig deeper into that and then just check deeper their cognitive load. So we only processed the part of the data 24, but it's good enough to show the story. So we listed the control group, the landmark, route, survey, visual cue is the AR simulation, and haptic suit. And this one shows the cognitive load based on their neural signals. And as you can see, the AR represented the lowest load, and the landmark method represented the highest load. So if we stop here, it looks very simple, right? Okay, so in the future, we should apply this augmented reality technology to the firefighters, because for most people that would induce a lower cognitive load. So we actually plot the landscape of each person in the lines. Each line you see here represents one firefighter. And if you see here, for this right line, this person, yes, the AR gave him a relatively low cognitive load. But how about this purple line? For this particular firefighter, if you check the cognitive load, when we gave him the AR method to find out the missing people, the load was actually higher than giving him nothing. So this is a perfect example showing that we should personalize the solution. We cannot just simply aggregate the result of 50 people and learn things from there and force everybody to use the same solution. And this curves is actually the information personality landscape that I described earlier. And you can see each person gave you a different landscape. Okay, the second thing we learned from our year 2 experiment is, can we predict the cognitive overload? So as you can see, this one shows the 1 hour worth of the data. This should be the left side of the brain and the right side of the brain. As you can see, once again, everybody is so different. So in here, we just want to see if we can predict the cognitive load. So we get just a small chunk of data, and we apply this machine learning method called long short-term memory, and we try to see if we can predict the main trend of the curve. The blue line shows the actual oxygen level, oxygen consumption level, and the red line shows the predicted or fitted line. As you can see, when this blue line jumps, it means this person started to use more oxygen in certain area, and that's indicator of cognitive overload. And the red line could predict that trend change just a couple seconds before that. But that's enough. That is enough for us to see, oh, now it's time for us to adjust the content of the information or switch from this landmark instruction to this route instruction just to reduce the person's cognitive load. And recently, we also try to focus on the hidden fingerprint, which is what we call neural connectivity. Most neural research, they focus on the isolated area of your brain. So like I mentioned earlier, prefrontal area, how much more oxygen that area is consuming. But what we found from our data analysis was sometimes is the correlation of different areas and how different areas of your brain dance together shows the pattern. Sometimes if your left interhemisphere, your left hemisphere and your right hemisphere, that correlation is stronger, what we call interhemisphere connectivity. It's indicator of cognitive overload. It means you have to use the resource from both sides of your brain to process the information. So this is something we are currently investigating. We found it to be very interesting, and hopefully we can integrate this fingerprint into our holistic cognitive load measure, real-time cognitive load measure method. So that is the quick overview of year 1, year 2 findings. And starting from this June, we will start our year 3 activity to prototype the system. So number one thing we are researching right now is what building information we should be using in the future. So it's more than just the layout, but also information about the building structure, information about the building material use, information about the current status. Because we found this information, all these pieces of information are important for firefighters to make good decisions. But meanwhile, with potential risk of overloading their cognitive process. And also, we are investigating if in the future we are using the side display, what is the best way to show up all the information. Maybe some information should stay there forever. Maybe some information should be changing. And for those changeable information, what is the best way to talk to our system, our algorithm, and to change from 2D to 3D, or to change them from landmarks to routes, etc. One particular challenge that we found, and we believe we found a way to solve it, is to tell what you are thinking. In reality, the information, wayfinding information can be totally mixed up and complex. For example, at the casino, we are showing the landmark, the signage, but also we are showing the routes using maybe different colors on the ground, different types of carpet. But also we probably also show you the maps of the casino anywhere. So we need to find out what format of information you are actually currently digesting, processing. So that's the way for us to tell, oh, what information is driving the high cognitive load, and we can stay away from it. But in reality, it can be challenging because yes, we can track your eye focus, but we can only tell you what you are looking at. We cannot see what you are seeing. What you are looking at is very different than what you are thinking yourself inside the brain. So we started to use this deep learning method. We gave the test subjects the pure stimuli of information, like 2D information, 3D information, or 2D landmark information, 3D map information. And we repeat that many times so we know, oh, so for your brain, when you see this particular information, what is the reaction of your brain? And then we mix up all the information. We start to see your brain activity is somehow the mix up of the fundamental brain activity patterns that you are seeing when you are seeing the pure information format. So we use this deep learning method, convolutional neural network, to decompose your brain activities and classify them into each pure fundamental base reaction, so we can know, oh, your current brain activity is mainly driven by that 2D map, even though you are looking at a mix-up of both 2D map and verbal instruction or at the lines on the ground. So this will be a very important function of our prototype system, that first to tell what information is overloading you, and then based on the information personality we learned from year 2, we now can adjust the information for you. And this is the overall system flowchart. We collect your brain activity, we build your information personality model, we tell what your current focus is. Without you telling me, we check your brain, and then based on this information personality model, we adjust the headset or the haptic suit device that give you the right information that to lower your cognitive load. So this is overview of our project, and just want to express our most sincere thanks to our collaborators from Brand Fire Department, from DoD Fire School, from Boston Fire Department, and of course special thanks to all the graduate students from the 3 universities. All right, so this is my contact information, and it has my office number and email address here. I welcome comments, and of course, if you want to collaborate with us, please don't hesitate to drop an email. Thank you, and have a good day.